So let's get started. So welcome back, everyone. So today we are going to be starting a new section on class on linear regression. Quite possibly a number of you have heard of this before, even seen some stuff about it. We'll try and walk through it from first principles, and so it should kind of and maybe go slightly beyond what you've seen before. And we'll get into ideas like cross-validation, which if you have seen it before, well, it's important. You can see it again. If not, it's a kind of super important idea. So let's quickly look at the schedule. So let's see. So we are here on the schedule, and if you notice, kind of a couple things to see. One, we have skipped. So chapter 4 in the book, chapter 4 in the book is a fairly fundamental chapter about distances, and that there are lots of different distances you can use to model data, and it's a modeling choice, and there's a lot of kind of cool stuff in that chapter. We're not going to cover it. This class, we're going to kind of try and keep things simpler and just use the Euclidean distance basically everywhere. The straight line distance between two things corresponding with the 2 norm of a vector, okay? But if you want to see a whole bunch more in that, that's in chapter 4. The data mining class goes through that chapter in much more detail, for instance. And kind of this kind of lecture in this section is really starting the point where we're going to start. We've kind of finished the very general background material, and we can now really start getting into the techniques used for data analysis and covering a variety of different settings. The first one being linear regression. We're going to start with this one. Before we move to the next ones, we kind of need to, after we introduce this, we're going to introduce a couple of new ideas. So cross-validation and then gradient descent. These are kind of analysis ideas in cross-validation, and then kind of algorithmic ideas in gradient descent, and these will be useful kind of to various extents later on in the semester as well. But we'll kind of we'll jump into this. So also homework 2 is due today at the end of the day. Hopefully you all have started on that. A number of you had already kind of submitted your homework. You'll notice also that the grades for homework 1 have been posted, and for quiz number 2. If you have any, there were a couple of delays kind of the first time going through some of these things, but if you have questions about those, now that the grades are posted what would be a good time to ask. Well, not right now in the middle of class, but we can, if there's a broad question we can do in class, but otherwise after class or on email is so great. So any kind of questions with where we are on the schedule? So good. So we'll jump back here. We're going to do some stuff on Collab today, kind of some actual experiments. The algorithms for these are very straightforward, and it helps to show them, I think. So we are talking about linear regression, and I want to start with thinking about what is the input to this problem. And we'll write the input as a set x, y, and x is uppercase, which is going to be a little bit weird today, but will make sense in the next lecture. And this is a set. You can think of this as a set of pairs, x1, y1, right? That's a pair, x2, so y2 up to xn and yn. All right, so we're going to think of these as pairs. Each in this lecture, each xi is going to be a real value, and each yi is going to be a real value. Okay, and so you could kind of think of the x here as a matrix that's an n by 1 matrix. Okay, and so in the next lecture, we'll extend this when it's not n by 1, but it's n by d or something like that. And then y we'll think of as a vector Rn, actually. Okay, and we'll, in this class, we'll keep this as a vector. There are extensions where this can be a matrix valued as well, but yeah.
Sorry, do you mind going down that trajectory?
Oh, yeah. This is a test now, see what my vertical is, huh? Should have done this before class. Gotcha. All right. Anyone see a plunger stick or it's really tall? All right, if you are at home on Zoom, you missed a really exciting jump. I got in the third try, which I feel pretty good about. Okay, it could have gone a lot worse there. So okay, all right, great. Okay, so we have these two types of inputs, and we're not going to treat them. You could think of this as just right. Could be convenient to think of this as like a single matrix, right? Think of this as x, y, and you have x on this side and y on this side. And sometimes you'll kind of write it that way. It's kind of unintuitive. So you think of them separately. Okay, so we're not going to do this. Okay. All right. So we're going to treat these separately. The x we'll say is going to be an explanatory variable, and y will be a dependent variable. All right, and the idea is that there's some model, some sort of function. There's going to be, and this is going to kind of be kind of a general thing where there's going to be some function that's going to go from, in this case, R1, and in general, this will be kind of RD here, but from R1 to R1, and these will be the xi's, and these will be the yi's here. And so kind of what we're thinking, what we would like with this function is that f of xi is approximately equal to the value of yi. What we'd like to do is understand a function. This will be kind of a model, in this case, where we're going to trying to let the values xi's, these xi values, to kind of, or that value in this case, one value, to explain the term yi. So yi somehow depends on the input xi. Okay. So this is what we would like to do. Okay, and in this kind of lecture in particular, it's going to be a so we're going to talk about, linear regression. So we're going to look at a linear function f. Okay. We'll get into nonlinear functions, but for now, it turns out the key is to understand the linear functions, and then you can kind of extend it to, oh, great. And then you can extend it to the nonlinear functions. Okay, so a couple of ways to think about this. You think of, again, now one thing it is useful to think about is to have the explanatory variables here. And I didn't just write x because we'll make this multidimensional kind of later on. And then you have the dependent variables here. Okay, and we're going to get a bunch of these. Each one, say this is xi, yi, it's a point, right? It's got x coordinate, that's the first coordinate, and the y coordinate is the second one, right? And it gives me, right, so the explanatory variable corresponds to here, and the dependent variable corresponds to here. This is a point, and I'm going to have a bunch of these points. I'm going to have n of them. Okay, and I'd like to try and have a function. Okay, now when I have a function, what does the function do? It maps the x-axis. It gives everything on the x-axis a value in the y-axis, so it could be some function which goes through here. Let's keep things a little simpler here for now. Let's say these are the data points, okay? And let's say there's some function which goes through, and it'd be nice if it was like this. So everything in the x value, I predict something in the y value here. This is the function f, okay? But we're doing linear regression, so this function has to be so linear, okay? So actually, we're going to want it to be a line. Linear means it has to be a line. This is a linear function, okay? And if you have a linear function where you have yi is approximately some function of xi, that means it can only take a very special form. It can have two values here. We'll call these a plus b. Okay, if it's linear, a line, it has to have two parameters. A is like a slope, right? This is like a slope, and this one is like an offset, right? So this is the value b. If I go to 0, then I say how high up do I go on the y-axis when I hit 0? Well, that corresponds with the value b, and a corresponds with the slope of this line. This is how you parametrically describe a line, and means we basically need to figure out what are these two values that determine our function, and figure out what is the best function we can get here, given that it's going to be a linear function. Okay, so this is kind of a mathematical preview. Let's look at a little bit of data and make this a little bit more concrete. Okay, so here's an example from the book. Okay, and you can think of this example as having kind of the two components here. Well, I switch colors a little bit, but this is going to be correspond with the height in inches. Let's say this is some people I've measured of their height in inches. I've corresponded their weight in pounds, right? And so I've got the weight here, okay? And so the height is the explanatory variable, and I think that if I know someone's height, I can predict what their weight is going to be. Not exactly, but I can get a pretty good idea of what their weight's going to be. Someone who's taller should probably weigh more, right? This is true. This kind of is probably a truism. So okay, and so I've got a bunch of data that's these x and these y values, right? So this would be x1 and this would be y1. x2, y2, up to x. How many do I have here? I've got 10, x10, and this is y10. Okay, and each of them corresponds with a point. Let's take this example. Let's look at this example right here. X5, x is 65 and y is 155. 65 and 155 corresponds with this point right here. Okay, so this row in this table corresponds with a point here. And each of these data things corresponds with a point, and we want to fit this line to go through here. And this should be, well, y approximately ax plus b corresponds with this line, right? And so this kind of is, in some way, the line that is can best fit this data in some way. Okay, so we want to find the line that best fits the data, and I'll describe what best fits the data means formally. But we wanted to kind of, it'd be great if it went through all the data points, but it doesn't exactly go through all the data points, but it's pretty close. Okay. All right, and to do that, we'll need to, again, we know it has this form. It has to be a line, so then we have to solve for the values a and b that find this line. So we'll come up with an algorithm to, given the data, find for the best choice of a and b that fits through this data. So one of the most kind of crucial things to understand about this that is not always kind of apparent the first time you see it is that kind of the most important kind of role of this is in this prediction of new data. Okay, and this corresponds with some value on the x-axis here. Let's say the whole point of building a function that goes from, right, we have some function of x equals a of x plus b. The point of having a function is to be able to do prediction. Okay, so it means I want to get in a new data point like this 69 inches, right? If I have 69 inches as a new data point, I would like to try and predict what the weight of someone who all I know is their height. All I know is their height. I think that the height is explanatory and that the weight is dependent on that, right? So I can somehow get some dependence. There might be other factors, but this is all I'm going to have at this point. And so I'm going to make a prediction. So how can I use this line to make a prediction? Right, so I'm going to figure out where, if I put the value 69 into my function, well, that's going to correspond with a kind of a point right here, right? And so that's going to evaluate this function. So I say f of 69, and this is going to equal something, let's say, I probably have the exact value in my notes. Is going to be about 182 pounds, right? And that's going to mean it comes over here. So given this kind of knowledge of the height of 69 inches, I'm going to use this model to predict someone weighs about 182 pounds. Okay, given this data. Okay, and so this is the basic premise here. Okay, and again, there's some underlying assumption that the data is drawn IID from some underlying distribution. And we're not going to get into that kind of too much, but we're going to think that the data comes from the new observation where we only have the height or the x value comes from the same distribution where we gathered data and we built this model from. So we hope that it generalizes onto this, so new data. Okay. So one thing that's important about this is that if we're to evaluate how well is this working, right? We're evaluating how well is this working. We want to say how close are the points on to the line, right? We want to say how close are the points onto the line. That kind of gives us a sense of how well this is working. And there are kind of two ways you could try and measure what's going on here. Okay, one way, let's pick a good color here, purple. All right. One way is to say, given a point, this point right here. Oh, I didn't get it. All right. This point right here, how close is it to the line? One way is, as we measured with the dot product, let's measure the distance onto the line here, right? So this might be a logical way of doing it. I say, how close is it onto the line? Turns out this is the wrong way to measure error in the set. The closest point from this data point, let's say this one was about, this correspond with this data point here, okay? And I tried to measure this data point onto the closest point of the line. That's not what I want to do. I'm going to kind of treat the X value as known. And so the model doesn't, there's actually the model says, I have a prediction for the X value, which is up here, right? So this would be F of 70. And we'll call this is X4, Y4. So this would be Y4 hat. My estimate based on the model of 70 is going to be up here, and I'm going to use the existing value of X4 of 70, right? So then the error is in this direction. I'm only measuring in this vertical direction in this Y coordinate, not in the X coordinate. I'm going to assume the X coordinate is right. I assume I know when I'm making a new prediction, I'm assuming I know what the X value is. All I care about is how good, given that X value, I'm predicting what the Y value is. Okay, there are other models that try and deal with both of these things, or we'll see later this projection distance shows up in like dimensionality reduction. We'll see that version, dimensionality reduction, the things that allow error in the X coordinates. We're not going to get into these in class. That ends up being, it's pretty rare you actually, in most data analysis, you actually want to do that. You need to get into pretty advanced things where that modeling kind of comes into, becomes important. So we're going to assume we know exactly the X value, and we're just going to predict the Y value. And so the error is entirely vertical right here. Okay. All right. So if we're going to take this and we're going to, so measure the error. Okay, we're going to do what's called the residual. Okay, so let's try and write this more carefully without the clutter of this drawing here. And basically this residual, so for a model, I'll call this model L. This will be our function from our function. It'll be a line. Okay, so I'll call it L. And so the residual on, so data point xi, so yi is going to be ri. Okay, this residual, and we're going to write this as yi minus yi hat. Remember, yi hat is equal to the function given these x value. There's a right. So this residual is how we measure the error. It's the difference between the true y value that we have observed and the y hat value, which is what is the one predicted from the model. Okay, and so And this is, again, we can write the model as this function, right, that maps from the x value onto the y value. We'll call this L because it's going to be a line. Okay. Okay, and so this is how we'll measure error of just one data point. Okay, and so the reason why, again, the reason why we want to measure error is because we're making predictions. We want to say, how good is this prediction on the data I have, right? If I have kind of a data value, so xi, yi, I want to know how good was it on that data point, right? And this tells us how good this, what this prediction was. So sometimes we'll use kind of an unsigned version of this, where you might take the absolute value of the residual. We'll eventually kind of end up doing that or squaring it or something like that. But for now, I'll define the residual as being the signed error. That way we can see what we'd like kind of in this prediction. Some of these data points have a positive residual and some a negative residual, and on average they should kind of cancel out, right? So that's kind of it's useful to think of them being signed, because then the average residual, it can actually be zero. That means that that's probably a good thing. All right. Another advantage of measuring error in this way, as opposed to the kind of this other way, right? We have this model. We have a data point, xi, yi, and we have the residual here, ri, versus alternatively, we can say the projected distance, right? This is the projection onto the closest point. Okay, so one useful thing to realize here is that the units of ri are the same as yi. Okay. Okay. This often is not mentioned, but kind of as a reason for doing it this way. But this is a really important aspect. If I were to use the green distance instead, this is somehow measured kind of in the distance, the x direction and the y direction at the same time. It's shorter. The green one is always shorter. That's the closest error. But it's somehow, but that's given the frame I've drawn it in, right? If we go back here, this is height in inches, and this is weight in pounds. Okay. Well, how do I then? What is the units of this green distance? What units does a green distance have? Yeah. Kind of height and weight. Yeah. So it's kind of you can't have a unit like, okay, so if I tell you a number like 12, do I say 12 inches and pounds, or yeah, so this isn't really a thing, right? So this was actually a trick question. There isn't a good way to define the units for this. Okay, so there's not a good way to define the units for this green distance here. Okay, so if you're going to do this, you have to somehow think of getting rid of the units first and turning this into like a unitless operation. You could try and normalize the data and do some other stuff to get rid of the units, and those leads to all sorts of kind of messy other issues that you often don't want to deal with. So if I just use the purple residual, I don't need to worry about that. The residual has units that make sense. The green one does not really have units that make sense unless I go through some other stuff with my data. Otherwise, I could, if I change this from inches to feet, right? Well, we did this in one of the examples in the first couple of weeks of class, right? Well, then that green distance changes, and it's going to map to actually a different point on the line. I'm going to get a different green distance if I change from inches to feet in how I measure the x-axis. which is pretty weird, right? That's probably not some property you want of how you measure error. I changed the units. I haven't changed the information. The information is exactly the same. I just changed the units, right? And my error measure is different, right? So that's kind of weird, right? The purple one does not have that problem. So that's why we're going to use this purple distance, the residual, which is just the vertical distance, just measuring the error in the prediction. Okay? Okay, cool. So this is kind of these kind of little things are often not talked about. Okay, this tells you how to measure error on a single data point here. Okay, but remember I had 10 of these data points, right? I had 10 of the data points. Each of them have a residual. How do I measure the overall error? What's the right way to measure the overall error? Yep. Yeah. So the overall error, one option would be to do this sum of all the RIs, right? And so I would like, so I could do something like I equals to n and sum these RIs. Okay, and the hope is that they cancel out and this error is going to be 0, right? So but I could have that the error, often I want to make the error small, right? So I could actually get some data set like this. Remember, I do Ri is equal to Yi minus Yi hat. Okay, so if I made the Yi hats going to be very large, right, like this. Okay, this is not the right fit. These are all of these values are going to be something which is all of them are going to be negative, right? All these are negative values. So that means that the sum of these is something which is negative. So this is less than 0. And if I move it further up this way, the error keeps going down. Okay, so this just minimizing, I'd like to minimize the overall error, and this is not giving me a good minimum of the overall error. But yep.
Did you just negate the sum of these squares?
Yeah, right. Good. So I measure the absolute difference, right? And there are kind of two ways of doing this. One would be to the sum of Ri and take the absolute values of these. Right now, as I move further away, they become more negative, but it's an absolute value of a negative, so it becomes larger. The other is that was suggested is Ri squared. Okay, and I can think of having an R vector, which is R1, R2, up to Rn, right? So this is a vector. And this one corresponds with the L1 norm. And this one corresponds with the L2 norm of this residual vector. Okay? And so these are both good choices for the error. And these are both used. It's much more common to use, so this one. Okay, so this is what we are going to focus on. This is called the sum of kind of squared errors, right? So I'm often going to write this as sum of squared errors of, say, given a data set xy and a function, right, which will be the sum of the residual squared, right, which is equal to Yi minus Yi hat squared These are all just saying the same things, just different way of writing it. So if you see me write it, sometimes it'll be convenient to write it one of these ways. And just so you're familiar with all of them, but they're all saying the same thing. Okay, so we're using this sum of the squared errors. Yep.
Except for key norms like that, you then have to take the root according to whatever power it is of the interrogation problem.
Oh yeah, great. Yes, thank you. Sorry, this is the 2 norms squared. So thanks, great. Yes, 2 norms squared. If on your homework, a number of people, I wrote kind of this expression, the some vector, and I took a norm and a subscript 2 and a superscript 2. The subscript 2 meant the 2 norm, and the superscript, they're like, what does a superscript mean? It's a great question. It means to square it. And once you hear that, it's probably kind of obvious, but when you are like, oh no, it could mean something kind of weird. Yeah, so it just means to square it. Yep. Great, good. So, okay, so great. So this one is much more commonly used, the sum of the squared errors. Why do we think we use, so this one, why do we use the sum of the squared errors instead of the sum of the errors? Don't have any thoughts? What have we seen sum of squared errors before in the course? Where do we see some of the squared errors before? Not in a linear regression setting, but we somehow had this 2-page derivation, and at the end of it, we said, oh, it's just the sum of the squared distances. Do you remember in the Bayesian inference part of the course where we assume that we had data and we were, and the data had some normal noise, right? The most standard form of the noise function. And we wanted to find the maximum likelihood estimate, the MLE, of the model of a single point from a bunch of data with normal noise, normally distributed noise on the data. Okay? And we derived it, we did this log likelihood, we simplified a bunch of stuff, we did this kind of, and eventually it said, well, the point to maximize the maximum likelihood estimate, you want to minimize the sum of the squared errors of this model, right? And this model kind of showed up there as kind of a single point function, right? We had a single point function we're trying to minimize, in this case, from the data. Now we're trying to minimize, we're going to try to find the best model again, and we're going to again see the sum of the squared errors. And in this case, the model is a line, right? So our model in this case is more complicated. L, remember, of x is equal to ax plus b. So I don't just have a single parameter, I now have 2 parameters, a and b, but I want to minimize the sum of the squared errors in the same way here. Okay, and there's a formal way to think about it, which I'm not going to get into in a lot of details in this course, but where I have a model, right, there's some underlying model here. Okay, so I have a model L, and I have some data points. And what the way of thinking about this is that there is, if I look at these residuals, I say that each yi is equal to some model of xi plus some noise. And the noise term is going to be normal error. It's going to have 0 mean, right? 0 mean. That's what the 0 here is saying. The mean is 0. An average has 0 error. So this would mean the residuals are going to cancel out if I added them all up. with the best model, but there's going to be some sort of variance here. And the variance tells me how big are these errors on average. Okay. And so if you were to work this out with this expression and to write out the maximum likelihood estimate of data that I assume came from this distribution where all the noise terms are independent, and I found the maximum likelihood estimate, it turns out it would be the values A and B, which minimize this sum of squared errors. Okay, so you can derive it. We are not going to derive it in the class. Okay, it's going to be kind of like the one that we did with the single point estimate, but it's more complicated because there's dependence between A and B. Okay, so we're not going to go and derive that, but just let you know there is a derivation in order to get this form, the sum of the squared errors, from this model, where we assume the data comes from a perfect linear function plus some noise in the y value. Okay, again, this noise only applies onto y, does not apply into x in this model here. So I can derive the sum of the squared errors in this way. Okay. That's one reason why. One reason why we do this sum of squared errors is we can derive it from the normal noise distribution. If you put a Laplacian noise instead, which is e to the minus absolute value instead of the distance squared, you can derive something like this though. Right, so this is still a reasonable model. The L2 distance is a little bit more intuitive to think about than the L1 distance. It's kind of like the straight line distance. I have to think about it in, this is now kind of, this is in an n-dimensional space. So I'm in this n-dimensional space. I want to find the straight line distance in this n-dimensional space. It turns out there's a really nice interpretation of solving for a regression, especially in kind of a higher dimensional setting, where we want to find the closest point in this n-dimensional space, and this will kind of this will come in handy there. Discussion of the normal equations in the book. I'm not sure if we'll get to them in this class or not. Potentially in the Slack lecture if we want to. So these are kind of another reason. The main reason is that there's going to be a simple algorithm for solving for the sum of the squared errors. Okay, so this is, kind of a lot of you are in the CS version of this class, and that's about computer science, and there is a closed form algorithm where I can solve for the optimal A and B. I can directly calculate the optimal A and B from the data X and Y. There is an algorithm for this one as well, the sum of it, the absolute values of errors. It is more complicated. It involves like dynamic programming, and you have to set some stuff up. Typically, you can solve them both with gradient descent, which we'll see a little bit later in a few weeks. But again, the one with the sum of the squared errors is easier to solve with gradient descent, and we'll formalize that later on in the semester. So again, this is easier to solve. So I believe that kind of the reason the sum of the squared errors is mostly so popular is that it's the algorithmic perspective. This is not just a statistics class where we're looking at how do you evaluate error, but we are going to build in kind of the idea that there are algorithms, and that is driving some of our choices in how to do the modeling. Okay, let's see. The Minecraft distance, yes. The L1 is called the Minecraft. Yeah, I joked like it's often called like the Manhattan distance, and I joked that it's called like the Salt Lake City distance, because we have much more of a grid in Salt Lake City than there is in Manhattan. They have these weird cross streets and stuff. But yeah, so Minecraft is probably more appropriate. It's the number of blocks where you have to, the distance to walk there in Minecraft. Yes, that's, although, wait, you can walk on an angle in Minecraft, right? My kids play this, but I don't. Okay. Anyways, assume you had to, how many blocks you had to move in Minecraft. Okay, yes. So I think that's pretty much Right, it's assuming you stay on the grid. Yeah. So, okay, great. So we're gonna focus on the sum of squared errors. Okay, and now we want to think of this problem. We can think of this as kind of this, this algorithm problem now. Again, the input is going to be the set x and y, which is going to be x1, y1 up to xn, yn, okay? And these are going to be in our n cross, our elements of R cross R, okay? Okay, and our goal is to, hold on, okay, is to find a linear function, ax plus b. So actually, what I want to actually do is the values a and b to minimize the sum of squared errors from my input to this function. Okay, so now I can write down the actual goal. Okay, I've got data and I want to find the parametric values that if I find the optimal values of these to minimize the sum of squared errors. Okay, and we kind of saw some stuff like this earlier again with the maximum likelihood estimate, and we eventually derived a form that looked like this. This is often the starting point of where most machine learning formulations start. They'll say, I have data, I have some way of measuring the error. It's often going to be the sum of the squared errors, or at least the sum of some sort of error over all the data points. Over all the data points is very often going to be the sum I equals 1 to n times some sort of error, typically squared. Okay, but somehow measuring the sum of the errors, I want to find the model which minimizes the sum of the errors, and this is how my starting point here. Okay, and then I need to solve for A and B. How do I solve for A and B, which minimizes this error? Okay. Okay, so it turns out I'm going to give you kind of a very simple closed form solution in this two-dimensional case, and then in the next lecture we'll look at, we'll see kind of two other ways of solving this. So starting in the next lecture, this one is particularly easy when x is one dimensional. Okay, when I just have one-dimensional x, so I just have one value for every x value of each of the data points. Okay, so this is the setup here. And get used to it. If anything is kind of confusing about this setup of the problem, we'll see something like this over and over again. We'll often try and take a problem and model it in this form, where we have data, we somehow measure some error over the sum of the data points, and we want to minimize some model described parametrically by some values. Then we can say, okay, what are the optimal values A and B? Okay, let me write the algorithm on the next page here. Solving for A and B. Okay, so the first thing we're going to do is we're going to it's possible to write this in one line of code or one line of mathematics, but we're going to write this as we'll break it down into a few steps here in this simple version. We're first going to calculate a value x bar, which is going to be the average over all the xi values. Okay. We're also going to do the same with y bar. Okay, so these are the average for the y values. Okay, and then we're going to kind of normalize these data sets. Okay, I'm going to call these the data, and I'm going to write these as X, uppercase X bar, which is kind of thinking of this as a set, where you have this, the first kind of thing about this first term is going to be X or X1 minus X bar, then X2 minus X bar. You know, it's actually going to be this vector, right, up to Xn minus X bar. Typically, I'd write vector as a lowercase x, but I'd have to introduce some new variable name. So I'm just using uppercase in this case. And we'll do the same thing with y. Y1 minus Y bar, Y2 minus Y bar, Yn minus Y bar. Okay, so what has this done? Initially, I had data that probably could have lied like this. These would be my data points. And so what I've done is I've identified the average X value and average Y value. This is X bar, Y bar. And I've basically just changed I've subtracted that from all the data points. And you can think of this as just shifting the axes. So now X bar, Y bar is at the origin of the axes. So I've just kind of shifted. I can think of having kind of some old axes before where this was the origin, and then I shift them, so now this is the origin, right? I'm subtracting it from all the data points. I'm not changing the shape of the data. I'm just having it so that it's running through the origin here. Okay. Okay. So now I've kind of centered the data. So this is normalize or to center this data. Okay. Now I can calculate these two quantities. Then I can say A is going to be X bar dot product with Y bar divided by the 2 norm squared of X bar. This is going to be my slope, right? This term A is going to kind of be the slope, kind of the average of how fast is it rising as a ratio again, right? This is just the dot product between 2 vectors, and this is just the 2 norm of 2 vectors. Okay, and then 2, I need to solve for B. Okay, this one involves the answer for A, and it's going to be Y bar minus A X bar. Okay. So this value B, this corresponds with the offset in the original axes, right? This is going back to the original axes. I know the slope of that green line that I had that went through the center of the data. And now I need to make sure that in the original basis, it still goes through the center of the data, so that if I go up, I give every Y value a little boost of B. It could be a negative boost if it goes lower, a little boost of B. And then if I go on that, it hits through this X bar, Y bar in the original data set. Yeah.
So AX bar looks
yes. These are lowercase. These are scalars. Yeah, great. Yeah, so for B, B is going to be a scalar value, just a single value. And so I need kind of single values there. And those are lowercase X bar and Y bar, where these are having all the data. Most of the work is here, right? And then I just need to solve what's the offset. The hard part is kind of the slope here. Okay, so this B is a little bit easier to interpret and to see why it's the correct answer. Once I've chosen the slope, I kind of want the model to pass through this red point, right? So that's what solving for B is doing here. What solving for A is kind of a little harder to see, and we aren't going to prove why A is correct. We'll see a more general algorithm next time, and we'll as we have time, we'll go through the proof of why that one is correct. But it's going to be a generalization of this to higher dimensional data. One way of seeing this is that this dot product, turns out you can write the dot product as x bar times the 2 norm of x bar times the 2 norm of y bar times cosine of theta. Okay, the theta, again, these are n-dimensional vectors, and this is the angle between those vectors in this high dimensional space, right? Where theta is equal to the angle between x bar and y bar. Okay, if you can imagine that. So this angle is kind of a correction factor that says kind of how correlated are these to each other. But then again, it's divided by the norm of x squared. And I think this is interesting to look at, writing it this way, because I can cancel this, right? And what I get left is cosine theta. Okay, so that cosine theta is some factor that is correcting for how correlated they are. The more correlated they are, the more similar pointing of a direction they are in this high dimensional space. I'm going to have kind of so smaller. Yeah, the more the angles are, I guess we'll have a smaller value for there, but don't worry about that. What I'd like to point out, again, back to our discussion of the units, is that now my solution for A is the ratio of the norm of y bar over the norm of x bar. Those both have well-defined units. Remember, this could be, remember the y bar was something like, this was the weight, and this was the height, right? So the weight and the height have these different units, but what is A doing? It's translating in between those units, right? So if I take a value, I'm multiplying something that has a height component, input inches, by A, and its units are weight over height. So that's translating between these units. And the cosine theta does not have any dimensions to it. Okay, so this allows me to translate between the weight and the height in here, and that's how I get a prediction that is from the height onto the weight. Okay. All right. Okay. So kind of the takeaway here is not to fully understand this, how this A steps gets to. We can derive the more general version of that later, but that is a closed form, a simple solution. I'm taking a dot product, I'm taking a norm, which is kind of like another version of a norm squared, which is a dot product, just x bar by itself, and then I'm adjusting for the offset. Okay, and so I can just calculate this with the sum to minimize the sum of the squared errors. If I had to do the sum of the absolute value of the residuals, I can't necessarily solve for it this easily. Okay, and so this, it gives me an algorithm. Okay, I couldn't hear, is the numerator of A bar, X bar, or the numerator is the top part of A is the dot product between X bar and Y bar. These are the uppercase vectors I got here. All right, so I have this guy is going to here, and this guy is going to here, and don't forget this guy also goes down to here. Okay. Yeah. Okay. Good. And those are n-dimensional vectors. And yeah. Okay. How are we doing? All right. So any let's good. All right, okay. So this is an algorithm, how to solve this. And this, if I solve for A and B in this way, I get the optimal kind of solution in terms of minimizing the sum of the squared errors. And hopefully this is fairly well motivated. You can motivate it by saying there is a linear model that as the height increases, the weight increases at a weight which is linear, but there's some noise in here. There's differences in different, in people and measurement error and other stuff going on. And I'll wrap all that into this noise term. And so it's kind of, this is kind of the spirit of where this is coming from. And kind of this idea of kind of having an input, deciding I want my model to look in a particular form, and I need to solve for two parameters here. And I can write down a cost function, right? So eventually we can think of this as there's going to be some cost function G of A, B, right? So I think X and Y are kind of goes into the definition of this function. I want to minimize the values at A and B. I want to then find the argmin of this function. This is going to become a common theme in the class and a way of thinking about these problems. Okay, one more Zoom question. Oh, nope. Okay. All right. Okay, at this point, I wanted to kind of go through an example in Collab. And then in the next lecture on Thursday, we're going to see what happens when X becomes multidimensional. Okay. All right. So again, we're also going to do polynomial regression. We're also going to fit nonlinear functions as well. Okay, we'll do both of those things on Thursday. Should be great. But for now, I'm going to jump to this Collab example. Okay. Oh, I think I have it loaded already. So let me reconnect here. Okay, so this one, your homework number 3, you're going to have to do a little bit more implementation than we've done before in the class. I'm sure all of you can do it. It won't be that hard. But I recommend hopefully you did homework 2 in Python. You got to warm up with NumPy because we're going to start using Python and NumPy to do some of these things, right? So the first thing we're doing is we're loading in NumPy, and we are, and I've loaded in 2 arrays. This is, I believe, this exact same example I had earlier, right? These are the same X and Y coordinates. And to start off, I've computed the average of the X and the average Y. Those are the X bar and Y bar lowercase, right? Okay, but it's kind of just looking at the numbers is less fun than plotting them. So we're going to use matplotlib, which is kind of the default way to do plotting. Python has a lot of great plotting functionality that actually goes beyond this. You can draw some beautiful pictures. We're going to try and stick with some of the more core basic stuff here, and that's all we're going to need. And so using this library, we can draw a scatter plot first, right? So let's just look at this data. All right, while that's loading. All right, so what have I done here? I've called PLT a scatter plot. Okay, and it's, so I've kind of, once it does that, it knows I want to start plotting something. It's going to kind of gather the things I'm plotting. I'm just going to take, remember the X and Y here are these vectors, these NumPy array vectors. And I'm saying I'm going to plot them, and then I'm going to increase the size of the dots and color them blue so you can see them a bit better. Okay, if I made these dots, yeah. So if you look at, then I drew the average too. I drew X average, Y average. Now that's now a single point, and I drew that one a little bit bigger, and I drew it in red. Okay, so it's pretty easy to do, and I do PLT show, and it shows me the plot. Okay, so pretty easy to do. I think much easier than, once you get used to this, much easier than Excel or all these other plotting functions where you need to go through a menu. All of you probably like kind of just typing out. This has become so much easier and more powerful in what you can do, and you can program this stuff. Anyway, so you can see these points. These are the same points we saw before. And again, we want to now fit this line through the points. Okay. Okay, and let's first go through this kind of closed form, very simple, like several step process to do that, right? This is, I've changed these arrays into the centered arrays from X and Y to X center and Y center. And if you notice, like in Python, it's not like, I don't know what you guys learned beforehand. I grew up on C, and you'd have to declare all these variables what they are. I just say it's equal this. It knows that it's a NumPy array, and I just solve for A and B. I do xc dot xc divided by xc, or xc dot yc divided by xc dot xc. I could have done instead the norm squared of this on this line here, but just as easy. And then I solve for B, right? The y average minus A times the x average. Okay, and then I can print these out. Right, so I print out the x and y average again for whatever reason, and these are A and B. Right, so it says, okay, so one thing it might be useful to do is the slope of A. This is saying for every pound, for every inch, you expect that someone is higher, you expect them another 8, every inch is like 8 pounds, 8.2 pounds. But the offset was something like minus 383, right? So that means if someone is 0 inches tall, they would have a negative weight. Is this a problem? Right, is this something I should be worried about here? Yeah, so someone could get one of these expressions. Yeah, so maybe, right? And sometimes you want to think about what these parameters mean, right? Now, I didn't have any data. If I go back up here, well, my smallest height was 60, right? So this is really far outside my data set. What does it mean for someone to be 0 inches tall? Well, there aren't really any people who are 0 inches tall. So this really isn't in our data. You think, well, as people grow, they start out smaller, and then, as they're born, they're not very tall and they weigh less. But probably down there, we're still predicting some value which is negative. Well, again, depends on this data. Maybe these are full-grown humans, and when they've, or at a certain age, and at that age this exists. But at that age, I don't have any people who are less than maybe 60 is in the right lower bound, but there's some lower inches, which is a lower bound, and I only need the model to work inside of the region of data. Yeah, it's good to ask those questions. I'm not terribly concerned here, and this in this case, this isn't real data. I think I made this data up anyway, so. But if, I could have been concerned there that wouldn't be realistic, and then I wouldn't have used this example. Okay. Okay, so this was a solution. I'll plot the line in a second. Yeah, so, remember our goal was to predict new data. So with someone who was 69 inches, we want to predict a weight. All right, so I put that into my function, right? My function A times X plus B, and X is 69. So I get a weight of 183. I told you it was 182 before, but let's say it's 183 in this case, okay? And that's my prediction. This is the power here, is that I expect if I get new data and I only get the X values, I can predict what the Y values are going to be here. We'll go through another kind of example of where that'll be useful kind of in the next lecture with multidimensional data. Okay. Okay. Oh yeah. So yeah, this line here, 5. This solving. This is traditionally not how you would solve this inside of NumPy or inside Python. There are many built-in functions that solve something like this. I've used one here that we'll use again in another example later on, I think in the next class, called polyfit. This will fit a polynomial function later, but I've set the parameter of this polynomial function to 1, which means that's linear, which means it gets us back our result. And so this is an example of solving this way with this this built-in function. And it gives me A and B, and it's exactly the same values, okay? As we saw before. Great. And then, yep, see, and, okay, and now we'd like to kind of plot this line. Okay, so let's go through. To plot the line, let me explain how this works so you get your mental model of what the plotting is doing. It's not quite like drawing, forcing, the way Python is plotting it, it's plotting a function, it's not drawing a straight line. So what I'm gonna do is I'm using this linspace command, and this is giving me kind of a vector, and I'm saying I want to plot a function between 60 and 72, right? That's what those first two parameters on the input is. And I'm going to have 17 of these, 60 and 76, great. And I'm going to have 17 different spots, right? Starting at 60, ending at 76. And I'm going to calculate a value for each of those, and then I'm going to plot this function, which will be the red line here, right? And the function I'm going to use is this line function. So I'm actually going to pass in this so I'm eventually going to pass in this function I call line, which I'm just defining up here, and it's so it's taking an h. H is now an array, right? And A and B are scalars, right? So this is really cool here. A and B are scalars and H is an array, and I multiply A times the array H, and what's the output going to be? It's going to be another array, okay? It's A times H. Okay, so this one probably isn't too hard to believe. This makes sense to do. I'm multiplying A times every entry in that array, and then I'm adding B. I'm adding a scalar again to that. It knows I should add that scalar to every entry in the array. It's an element-wise add of the value B. And I don't have to write this out in a linear algebraic form. Like NumPy kind of recognizes that this is what is going on here. And so this makes it very easy to write things like this, right? H was all these possible X values I'm going to plot, right? And A and B are these scalars, and I pass it through this model, okay? Okay, then I'm going to redraw my scatter plots, including kind of I think the average point here, which I've just copied down. And then I'm going to write, and then I'm going to plot the scatter plot with my prediction for the value 69, right? Yeah, question?
What are the values?
The values, so if I print out here, let's do it down here. Print, just so you see what this is. All right, so if you want to see what is the linspace, it is these values 60, 61 up to 76, right? It's a way of generating, it's kind of a shorthand, which is very useful, is I'm going to pick a bunch of points along here, and I'm going to plot a function that's going to be I'm going to evaluate a bunch of values. I'm going to connect them by little piecewise curves. It doesn't need to be a linear function in order to plot this way. We're going to plot polynomial functions on Thursday using the same mechanism. And there it's just going to, the plotting function does not know it's a line. The plot function thinks it's a piecewise curve, a piecewise linear curve, where I'm just evaluating at points, I'm connecting each by line segments. And the more resolution I get, if I put let's see, I put kind of 50 in here instead, it's going to plot the same thing. It's plotting at a higher resolution, but it's not going to matter because it's a line. Why is this taking so long? Okay, so it plots the same thing, but my H is now, okay, I want 50 values between 60 and 76, and it says, okay, I move 0.326 every step in order to get these 50 values. All right, good. Yeah, no, it's good to have a mental model of what how this function is, spline function is working here. Yeah, right. Lin space there. So the points are so linearly spaced. Yes. Okay. And then so yeah, so I can evaluate at 69, get the black point, and it turns out it's right on the red line. To plot the line, now I just pass in h, which is the x coordinates. Remember, h is the x coordinates, and line is now all the y coordinates. Okay, so again, I'm just plotting PLT plot. That plot's not a scatter plot, but it plots this line plot. And it's just, and I'm calling it to a red dash. This is controlling the style. I could do something else here. Let's see if I do, let's do L plus. Let's see if this gives me some different. I think this will give something else. It might draw a plus at every point it evaluates. Right, so now it's drawing a bunch of pluses along here, right? But if I just want to draw a line so it's connected, then I put the minus symbol and it connects all these together. Okay, so that's how you generate this. Ultimately, it's pretty simple, and this example will actually generalize in the next lecture. Okay, great. I have a little bit of time for questions, and there's some stuff here I didn't go over. I was supposed to do this a week ago. So let me just mention that there are a couple of commands are in particularly, yeah, so a couple of commands that might be useful. This matrix inverse, we're going to need a matrix inverse to solve the more general version of linear regression. We go to higher dimensions, polynomial regression. We need to do a matrix inverse, right? We define this operation. It's, you can calculate, this is kind of, you kind of get into like deeper computational linear algebra, how to compute a matrix inverse. Oh, I didn't load all this stuff. Great. Okay. I need to reload. Just get C. Where's? Okay, good. So I've got a matrix C -5, 2, 3, -1. Okay, and I took the inverse, and I got back some kind of strange looking stuff here. Okay. Okay, no, this is the inverse. So C, well, let me also print C. Okay, so this is C is 1, 2, 3, 5. The inverse happened to be a pretty nicely defined matrix here, is -5, 2, 3, -1. Okay, and I'll change that, and we'll see what happens in a second. The inverse turns out to be a pretty simple flip here with some minus signs. And if we multiply, remember, if you multiply the inverse by the matrix itself, you should get back the identity matrix, right? This is supposed to give me back the identity matrix on the last line here. But what I'm getting is this other matrix here, which it doesn't quite look like the identity matrix. What's going on here? Yep.
You got ones in the back. You said really small numbers.
Yeah, right. The diagonals, those are actually ones, right? The 1.00000 e to the +00, right? That's scientific notation. That's saying that is actually one. It just wrote them all in the same notation. Off the diagonal, the 4.44, but that's e to the minus 16th, right? So that's the first, I think that means the first 16 values are all zeros, and this is the 17th decimal. And similar to the other ones, the 17th decimal is a 2, the first one 0. So those are essentially zero. Sometimes you get this back, and you need to be satisfied that that is close enough to identity. Okay, if I put a, let me just quickly change this 5 to a 17, and let's see what happens. Okay, I'm getting back something a little bit stranger in this case, but you know, I'm still getting back a matrix inverse, and this one's even closer to 0. It's even written in as 0 now. Okay, great. So we'll stop there, and we'll do. Don't forget to turn in your homework, and we'll kind of generalize this on Thursday. Yep.
I'm kind of confused. I've done all the other problems except for one. I'm kind of confused. I understand what it's saying. It's like
tell them, hey, I'm talking with another student, and I'll get to your homework question. I see it's.
All right. Okay.
I'll let you know.
Sure.
Yeah.
Okay. Yeah.
You are next in line. Okay. So I want to do. So it's C. Let's see what you want to write here. Print. Let's just write in a print command. You want to do C dot the inverse.
No, I got to the inverse matrix for the C dot.
Oh, the inverse. Yeah, so then I can do L, yeah, so I should be able to do this as well. Because this needs to take in a square matrix, and because C is squared, then I can do this, right? So this is the inverse of C dot C,
Okay.
right?
So if I do this inverse and it report here, that means this matrix is not invertible.
Correct. Yeah, yeah. If it's non-vertible, let's do an example. I've got some matrices like A should not be invertible. So let's do L A inverse of A here. Right? It's going to give me an error. Oh, that's because A is not defined. Okay. Where did I find?
Here.
There we go. Right. So A is a 2x3 matrix, right? Okay. So now, okay. So what it says? It says,
Must be square.
yeah, it says must be square. It's because it's not square.
Okay. That's-
Yep. Okay, great. Steven, let me see.
Yes. So I have a question, like since like in the homework, like the question for F, it said that which matrices are invertible? Like, I mean, like does the matrix refers to the like matrix A and B, or just like everything like the matrices from the 4A till 4E?
Yeah, I wanted you to look at for A and B. Yeah, particularly
Oh.
those two, A and B. Yeah,
Oh, just A and B. All right, I see.
yeah.
And also, like, how do I report for the question 4? Like, I just report like the output, or both I have to include like the code and also the output?
Technically, you just need to report the output. I recommend everyone to include their code, even just like take basically a screenshot of the Python. And, if you're doing it in Collab, just create a screenshot and include that in the write-up. That way, if you did make a silly mistake, we can give you partial credit.
All right, I see. So I just need to take a screenshot of the from the Collab and then send it to answer number 4. That's it, right?
Yeah. So if you do that and your things are like labeled nicely, like you say 4A, 4B, you can write text inside the line of Collab, then you can just kind of paste, include that into your final document, however you want to do that.
All right. Okay. All right then. Yeah. Thank you so much.
Sure. Yep.
All right.
Yeah, that's what I recommend doing. I think I posted on Canvas that, yeah, but I just recommend just taking